subject which we are going to do is mass transfer operations 2. Okay, so from previous lecture we got to know about Rolle's law. Okay, how it is important for distillation. Okay, how it shows about how it is concerned with the vapor liquid equilibrium. Okay, now the next law which is important here is Dalton's law. Okay, see the in exam now your level is that high that they are not going to ask you simple questions based on Dalton's law or Rolle's law. Okay, it is just to understand. Okay, now here you have to relate thermodynamics with mass transfer also. Okay, try to study by relating thermodynamics with mass transfer. Okay, because see at the end what is thermodynamics? You can say thermodynamics is like a boss. Okay, it sets, it defines, it gives you some certain set of rules which other subjects like heat transfer, mass transfer, okay, those subjects which follow it. Okay, so in detail vapor liquid equilibrium, Rolle's law, Dalton's law, how it's important. Okay, that would you will study in thermodynamics, so try to learn the subject side by side. So now moving on with Dalton's law. Okay, so what does Dalton's law state? It states that at constant volume and constant temperature, the total pressure exerted by gas vapor mixture is equal to the sum of partial pressure of components present in it. Okay, here at constant volume and constant temperature. Okay, if see about pressure, you have to know about this, that pressure, you know, from if you're considering ideal gas, okay, PV is equal to nRT. I can say that pressure is directly proportional to temperature. Okay, so you have to be very specific here. What I'm doing, I'm keeping my volume and temperature constant. Okay, it's but natural. If I will change the temperature and volume, then I can't define it. Okay, at that steady point I have to be specific that I'm keeping my volume and temperature constant. Okay, so the total pressure which is exerted now, that is equal to sum of partial pressure of components present in it. Okay, now we saw what was partial pressure in last lecture. Okay, so moving forward, hence I can say that my PT, that is total pressure, is equal to PA plus PB. Okay, your PA is partial pressure of A and PB is partial pressure of B. Okay, you can see from example. See, all the bottles are same. Okay, volume, it means I'm keeping my volume. Okay, so you can see blue, purple, yellow. Okay, these three are different gases and it has individual pressure. Now see, in total pressure, okay, in the fourth bottle, when your all three components are present, then we are talking about total pressure. Okay, so you can see the definition how partial pressure works actually. At constant volume, okay, if my volume is same, then if I'm separating individual gases from the fourth cylinder, okay, which is all gases, and I'm placing them in three different containers of same volume as that was of total pressure container volume. Okay, so at that time, of course, the like 300 kilopascal, okay, that is pure A gas. Okay, so the pressure for 300 kilopascal container, okay, for my blue container which is having A gas, okay, blue gas, that is the total pressure here. Okay, for that container it is total pressure. Okay, now but if I'm mixing the three together, okay, you can see now all my blue, purple, yellow gases are together, but I'm keeping the volume. Okay, the initial condition, that was volume same. So now the pressure of that individual gas would be partial pressure. Okay, so you can see how addition of these three has gotten me total pressure, that is 1350 kilopascals. But in that container, your partial pressure is what of blue gas? It would be mole fraction into total pressure. You will see further. So you can see all three gases, its individual pressure was like 300, 600, 450. Okay, those were when they were individual, when they were in pure state. Okay, no mixing was there. And what volume was same. Okay. And now when I'm mixing them, keeping the volume which was initially same, so I can now say that the pressure that is exerted by those gases in the fourth cylinder, okay, when they are in mixture, that is its partial pressure. Now, for an ideal gas or vapor, the partial pressure is related to mole fraction of the component in gas or vapor phase. Okay. Now look at the fourth container. Okay, the fourth cylinder in the 1350 kilopascal pressure one, where all three gases are there. So here the partial pressure, you can say that its mole fraction, it is a product fraction I have given. Okay, for blue gas, suppose it is XA, and your total pressure is what? 1350. So when you get to know the mole fraction, okay, so that would be equal to 300 kilopascal. See, so I can say that, yes. So here also, see, gas A, B and C, when they were individual, its pressure was PA, PB, PC. Okay. Now in fourth cylinder, when all three are in mixture, okay, so that total pressure is equal to partial pressure of all the gases. Okay. When they are mixed together, then we introduce the term partial pressure. Okay. When they are in mixture, then the term is introduced, that is partial pressure. When they were kept in separate cylinders, okay, when they were kept in pure state, so at that time it was their individual pressure. Okay, but when they are in mixture, the term now partial pressure is introduced. So in mixture, I can say that the partial pressure is equal to mole fraction of A into total pressure. Similarly, I am defining all other gases partial pressure. Okay, you can see. So what is PA? That is equal to YAPT, PB is equal to YBPT, and PC equal to YCPT. Now, but the gas A, okay, where red dots are there, okay, when it is in pure form, so what would be my YA? That would be 1. So I can say for that cylinder, okay, when your gas A is only kept, when it is pure, so I can say my PA is equal to PT for that cylinder. Okay, okay, because YA is 1, it is pure. Similarly for B, YB is 1 when I'm talking about the second cylinder, when only my gas B is there, no other mixture is there. So that is again YB is equal to total pressure. So for that cylinder, that pressure is PB is total pressure for that cylinder. But when I'm mixing all three gases, okay, in the fourth cylinder, now you need to introduce your term mole fraction. Okay. So from Rolle's law and Dalton's law, okay, what I can say, in Rolle's law you saw the definition of partial pressure. Okay, it is product of liquid phase mole fraction into vapor pressure of that component in pure state. Hence PA, again last lecture I told you, your vapor pressure has a description of PA sat and PA 0 also. Okay, so what is your PA? Your PA partial pressure is product of liquid phase composition into vapor pressure in pure state. Similarly for B. Here let's take example like A is my more volatile. Okay. Now from Dalton's law, what is your total pressure again? Your total pressure is summation of partial pressures. So hence instead of PA partial pressure, what I am substituting? I am substituting the definition which we had from Rolle's law. Okay. PA dot PA0 dot XA plus PB0 dot XB. Okay, the product. Now, as we know that, okay, here I am talking about binary mixture. Okay, hence I have taken only two components. Again, what is binary mixture? Mixture of two components. Hence XA plus XB equal to 1. When I am talking about multi-component, then it could be XA plus XB plus XC plus XD up to many components. How many components are there? But note this, okay, your mole fraction, the summation of mole fraction of all the components will always be equal to 1. Now, as I have taken example of binary mixture, hence XA plus XB equal to 1. So, I can relate my XA as 1 minus XB, okay, or vice versa, XB equal to 1 minus XA. Okay. Also, yeah, again from Dalton's law, what is your PA? It is YA dot PT and PB equal to YB dot PT. YAPT is equal to PA dot XA. Okay, from this is your standard equation with which you can calculate many of your sums. Okay, like in exam they can ask you, find, you have like they have given you liquid phase composition, okay, and they have given you vapor pressure. Now total pressure is also given, so you can find your YA, vice versa you can find your PT also. Okay. Now moving on about relative volatility. Okay, this is the next topic which you will study, relative volatility. Now before studying relative volatility, we must know what is volatility. Okay, the exact technical definition. So it is defined as partial pressure of any component to the mole fraction of that component in liquid phase. Okay, so volatility of A is my partial pressure of A up ratio, this it gives you idea of measure of separation tendency. Okay. Now, in order to separate a binary mixture using distillation process, there must be difference in volatilities of the components. The greater the difference, the easier it is to do so. A measure for this is termed as relative volatility. See, we discussed in first lecture that distillation is a separation process, okay, which requires a large amount of heat. Okay, so it is where it has to be economic. If you have to select this process to do, it must be economic also. So when we are using distillation and separation process, okay, so if it is viable, it is okay to use it or not, that totally depends upon the relative volatility. Okay. Now, because you are separating your volatile components, okay, what is at the end your crude, okay, crude or any other mixture, okay, you have to separate it. But take example of crude, okay, it is mixture of many volatile components, okay, but you have to make sure that there is difference in volatility. Then and only then your components will separate from each other. So relative volatility, what it shows you that what is the difference between my A, B component. For example, taking for binary mixture, okay. If the difference between volatility of A and B is more, then it is suitable that okay, I'm using distillation process to separate them. Now suppose A boiling point is 80 and boiling point of B is like only 74. Okay, so there is only a difference between 6 degrees Celsius. So it is, of course, it is possible that there will be impurities present. Okay, there would be mixing of A and B components in vapor phase and liquid phase also. So hence we need to know about the relative volatility, okay, to know if separation is possible or not. So I can say my relative volatility as ratio of PA upon XA to PB upon XB. Okay. So see here, now what I am doing, I am representing my XB as 1 minus XB and YB as 1 minus YA. Okay. So that way I can do, if suppose only I am given YA and XA composition, I have to find relative volatility. So see, I am manipulating YB as 1 minus YA. Now if suppose I have been given partial pressure only and total pressure. So see, from how I can use my Rolle's law. Okay, so this is all derivation. So at the end, what you have to remember is the formula which is last. YA is equal to alpha AB XA whole upon 1 plus XA into alpha AB minus 1. Okay, so you can see Y versus X data can be generated over here. Okay, that we would study when we will take into account a question to solve. But for right now, you have to learn this by heart, that what is your final relation between y and x. Okay, ya is equal to alpha ab into xa upon 1 plus alpha ab minus 1 into xa. Okay, so see, I have represented my relative volatility alpha ab is equal to pa upon pb also. Okay, so now here don't try to remember it, okay, but try to be thorough with the derivations, okay, like how you can substitute at instant. Now when you will practice the derivation, you will of course by after 2 to 3 times you will remember, like okay, if only partial pressure of A and B is also given to me and I have to find my relative volatility, I can use this formula. Now when alpha AB is 1, then separation is above 1, sorry, then and only then separation is possible. Okay, now of course see, try to relate. Okay, only taking example of partial pressure of A and B. See, if alpha is equal to 1, it means PA is equal to PB. My partial pressure of A and B is same. It means when I am providing heat, okay, both will be in the vapor phase at same time. So both will be in the vapor phase, so it is no meaning. Okay, when I am taking out the vapors and distilling it, I will get the same solution again, because the composition, okay, the vapor phase composition, whatever of A and B is there, when they are condensed, same would be there that in liquid phase also. So if my alpha is 1, my relative volatility is 1, it means both are same volatile. Okay, both are equally volatile. So in that case, I can't use distillation as separation process. So yes, now so what is the gist which we got, that for distillation, okay, to use distillation, your alpha, your relative volatility must be compulsorily more than 1. Greater the relative volatility, what it shows that there is a big difference between boiling range of A and B component. Okay, it can say talking about, let's say example, alpha is equal to 12. It means my partial pressure of A is 12 times that of PB. Okay, so you can see the difference in volatilities. Like A will is so volatile that it will vaporize very fast, and you will get your pure A when you are condensing the vapors. Okay, now this equation y is equal to alpha AB1, how you can use, okay? So for different values of x and known value of relative volatility, I can generate my xy equilibrium data. Okay, for an ideal system, the volatility is equal to vapor pressure of pure component. Okay, when I'm talking about pure component, okay, and the system is ideal, okay, then my volatility is equal to vapor pressure. It's but natural. We saw if pure component is there, it means your mole fraction is what? 1. Hence your vapor pressure is equal to partial pressure. Okay, see. What was the definition of partial pressure from Rolle's law? Partial pressure is equal to vapor pressure into mole fraction of your more volatile component or any component. So if I'm talking about pure component, and of course when Rolle's law is applicable when I'm talking about ideal system. Okay. Now just learn this